So today we are going to be introducing open channel flow. And specifically, we're going to be talking about uniform flow, which we'll get to in a second. But first, our learning objectives. We're going to list two main differences between pipe and open channel flow. We're going to define the three flow classes, which we actually just looked at for kind of distinguished by spatial variability, meaning longitudinal variability, downstream variability of flow depth. How does flow depth change downstream? We're going to list the necessary conditions for uniform flow. How do we get uniform flow? In reality, we really never get uniform flow. It's just a nice approximation that allows us to model things a little more easily. We are going to state the conservation principles and assumptions how is your friend and full is the thing assumptions. I don't know if anyone is friends with a principle, but that lead to uniform flow slash Mannings equation, which we will use to evaluate uniform flow. And then finally, we're going to use Mannings equation, which we have introduced already for pipe flow, but really it's an open channel flow equation to calculate the velocity or discharge under uniform flow conditions and calculates normal depth. And we'll define that obviously when we get there. First, let's look at the difference between pipe flow. Can I get a pen here? Now we're going to compare open channel flow with pipe flow. Which one's better? Yeah, good answer. Open channel flow is way more fun. Open channel flow has more fun. Okay, what do we know about open channel flow versus pipe flow? How does flow happen in a pipe? Pressure. Okay, so pressurized. And we know that it's driven by pressure, right? But it's also driven by gravity. Yeah, gravity is playing a role there, right? Because water has weight because of gravity. So gravity and pressure drive flow. And the other thing that we'll just note is that the conduit which is the pipe, is flowing full. And that's an important distinction because we're going to see some situations where we have a pipe, but like a sewer pipe or storm sewer, but it's not going to be flowing full. And so we can use open channel flow calculations to evaluate the pipe flow. So conduit not flowing full. And then we talked about when we looked at the flume, we don't have pressure, right? So we have what's called a free surface, free to the atmosphere. And the flow is driven by what? Gravity. You can't push water necessarily. You can splash on, but you can't push water down a river. So gravity is essentially pulling it down the river. Okay. Great. So the next thing we'll talk about is different kinds of flow classifications. And this is the spatial variability or downstream variability of flow depth. So first we're going to start with uniform flow. That's what we're going to mostly be talking about today. And what that looks like is if we have channel moving downstream, we got this water surface that is going to be parallel to the bed. That's parallel. Just take my word for it. And so as we move downstream, we have the same flow depth, H1, H2, and H1 is equal to H2, V1 is equal to V2. The specific energy, which we use the letter E, E1 is equal to E2. Everything's just kind of nice and kosher. This doesn't mean we're conserving energy. I guess we are essentially, but what that means is that as you go downstream, gravity is driving. This is not like a closed system, right? You always have gravity adding energy into the system, maintaining that head over time. So uniform flow, the flow depth is not changing downstream, and so we'll write that out. So ds downstream. As you move down the channel. And what else do I want to say about that? We have to have a prismatic channel. What does prismatic mean? It has a shape. It's like a mirror. Prismatic. It could be any shape as long as it's a mirror. So that's just prismatic. The next type of flow, and we'll talk about this on our next lecture, is called rapidly varying flow. Or RVF. And for rapidly varying flow, we're saying the flow depth changes abruptly. Downstream. An example of that is our weir, where we put a little weir there, and we've got flow coming down, And I'll just extend this so we can see what happens to the flow if we were to have channel down. So flow is here, it hits the weir, and then it comes down like that, right? So there's this rapid change in flow depth. And one of the things we're going to do with rapidly varying flow is think about the relationship between the energy here and the energy here. And under rapidly varied flow conditions, as long as we're not going through a hydraulic jump like we did before, we can assume over a short distance that there's minimal energy loss, and then we can compare the specific energy from one point to the other. So this is where critical depth comes in. We'll talk about that a lot. The last type of flow, and this is actually the most complicated, is gradually varying flow. GVF, like it's gradual. Why is it that complicated? Because what it means is this is kind of the most realistic type of flow that best, when we think about the equations underlying gradually varying flow, they most accurately represent what we see in the natural world. Even in that flume, we saw that the flow is changing, the flow depth was changing downstream. In a river, in a canal, that changes width and slopes. Your flow depths are going to change from one point to the other. So flow depth changes gradually downstream. And what does this look like? Well, in a natural river, we get this kind of pool riffle type of profile as you move downstream. So we have kind of fast and shallow over the riffle, then we get to the pool, and then it's kind of like deep. If you've paddled the river, you've experienced these. And so the depth is changing in these different locations with time. So deep and slow in the pools, fast and shallow in the riffles. And then we also have rivers that just change their width over time. So we have kind of a meandering river from the plan view. Maybe it's like wider over here and then narrower and wider. So here we're going to have shallow conditions because it's broader. Here we'll have deeper conditions potentially. So maybe this is your pool. Got a riffle right here, riffle, pool, riffle. So depending on the whole setup of the channel, you're going to have more gradually varied flow conditions just because it's a natural channel. Even ditches will be like that too. Let's get into uniform flow. What's this all about? We're going to start with kind of like a free body diagram. Okay, we're going to have a water surface that's parallel to the slope of the channel. And then we'll also note, so if we have, let's see here, I'm going to draw these vertically. It's going to, the slope is so negligible in flows that this is a fine approximation. And then we'll note that if we say I'm just going to introduce it here, specific energy. We're going to talk about it more later. So E is equal to V squared over 2G plus Y. That's our energy for open channel flow. And we'll note that our specific energy, I shouldn't have, I wrote E1 is equal to E2, like I shouldn't have done that because you can see how it's going down, right? We're losing elevation. So elevation is part of that, but we'll get into that a little bit more later. So this is our energy grade line or the slope of our energy grade line, and it's parallel to the water surface. So this is delta E. And then we also have the slope of our water surface. And then we have the slope of the bed, which is S naught. I'll note that we have an angle here, which we'll call theta. And what else? We'll also note that if we look at well, I guess we'll get inside in a minute. Okay. Okay, so this is what's going on now. We're gonna think about, so we've got water flowing down, we got the depths are the same over time. We can call this energy, this is the slope of the energy grade line. So EGL, right, is equal to P over gamma plus V squared over 2G plus Z. And, you know, if this is our datum, we can just say this is 0 for our datum. So Y is our Z. This will be our hydraulic grade line, which is equal to P over gamma plus Z. And we'll note that P over gamma is going to be equal to the depth, right? So the depth is just our pressure. You go to the bottom of the channel, that is the overall pressure from the water. So we do have pressure in there, but it's not necessarily driving the flow. Okay, so now we're going to go to thinking about the forces acting on this. And we're just going to look at a prism of water. Or a little chunk of water right here. And we've got a pressure distribution, just a hydrostatic pressure distribution. So we'll just say force of pressure 1 force of pressure 2. We're gonna kind of finish this out where we've got, we'll call this the X direction. And we'll call this the Z direction. We've got some length that we're evaluating. We have the weight of the water. We've got our little angle theta. And what other forces do you think are acting on this water? So we're talking about the pressure. Is there anything else happening in this control volume? Yeah, there's going to be some friction, right? There's always, we always have to think about friction. So we'll call that force of friction. And it's acting against the water. It's just the bed, the water kind of moving across the bed. So we can use our conservation of momentum to evaluate this. And what is the conservation of momentum? Sum of forces, and we'll evaluate this in the X direction, is equal to rho Q V2 minus V1. So the sum of forces is equal to the sum of the flux of momentum through the control, to the two control surfaces. So if this is 1 and this is 2, we're thinking about that. So let's look at our sum of forces. And we say we get force of pressure 1 minus force of pressure 2 minus the force of friction. And then we get the weight force, right? And if we want the x direction component of that, that's going to be weight sine theta. And then all of that is going to equal this rho q v2 minus v1. What is this term going to be? It's going to be 0 because v1 is equal to v2 under uniform flow conditions, right? We're not changing velocity, so there's that's equal to 0. So everything, quote unquote, is in balance. All of these force terms are in balance. These are going to be equal and opposite the two pressure terms, so we can cross those out because the flow depth is the same. So what we end up with is that the force of friction is equal to weight sine of theta under uniform flow conditions. We can extrapolate this out a little bit more. So the weight is going to be equal to the specific weight. So this is weight over volume times the volume. So that would be our cross-sectional area. So that's going to just be the area of the flow times the length times sine of theta. And for small theta, sine of theta is approximate to tangent of theta, which is equal to x over y, or sorry, y over x, sorry. Which is equal to our slope. So S naught is just the bed slope. That's rise over run. And so we'll plug that in. And so say gamma A L S naught. All right, so we're gonna hold that one for later, and we'll bring it back in just a second. This is going to be the term for our weight in the x direction. Or sorry, force, weight of force. And then now we'll look at this friction force term. So F sub F. And we get, when we think about friction, what is actually happening here is we have shear stress, which we call tau naught. So shear stress being imparted on the kind of area of the bed. So we have this slope, but really we're looking at a channel here, right? And within that channel, we have this water. And that friction term is acting along this wetted perimeter, which also has a length L kind of across that. And so the area in that term, so if this is shear stress, this is force over area times area, we get force out, we get force back out. Then we can say this is tau naught times, we're going to call this P here, this wetted perimeter. So P times L. That's going to be our area term. P is wetted perimeter. We're going to see this term a lot. Tau is shear stress. Okay, and then we're going to make a little bit of a jump here. And we'll say that shear stress can be approximated by this term, and this is just some kind of engineering hydraulics that happens. V squared, so gamma V squared over C squared, and this is called Shazy relation or Shazy equation. And this is, how do we approximate shear stress? Well, it's approximated by velocity squared gamma divided by this coefficient. This is the Shazy coefficient, which is based on the kind of type of material in the bed. So we're going to have to take that as faith. You can read more about it in your book. And we will plug that in for shear stress up here. And so now we can say our force from friction is gamma V squared C squared PL. So now we're going to remember we're saying that our friction force is equal to the weight sine theta. So we're going to bring everything together. And so we're going to say gamma V squared over C squared PL is equal to that weight sine theta, which we extrapolated out to be gamma L A S naught, which is our bed slope. We can cross some stuff out, gamma L, and then we can solve. And what are we interested in solving for? Well, we want a relationship between velocity and bed slope and depth and all that good stuff. So what we're going to do is solve for V. So we'll say V is equal to this Shazy coefficient times the square root of A over P S naught. Or define a new term. I think we talked about this in pipe flow, but this is called the hydraulic radius. And that's equal to A over P. And it has units of length. So area is length squared, wetted perimeter is length. When you divide the two, we get that. So now our simple equation is V is equal to C square root of R S naught. A very simple equation, but very powerful, because if we know the wetted perimeter and the slope, we can calculate velocity, hence discharge, because area is in there. If we know velocity or discharge, we can calculate the wetted perimeter or depth, because depth is embedded in this area and wetted perimeter term. So a really nice equation. This is a kind of a European equation. They all came out of Europe originally, but in America, we use Mannings equation. Just has a very similar format, but not quite the same. So we'll call this the Shazy equation. It's empirical, meaning, so it's a little bit of both, right? It's fundamental where the physics kind of work out, but this coefficient, anytime you have a coefficient, you have to look it up in a table because it's calibrated based on experimental data. And therefore, we ultimately call this an empirical equation, just like the Hazen-Williams equation, that sort of thing. So this is kind of like Hazen-Williams, except for open channel flow. So I'm going to introduce the Mannings equation. We'll use it in a simple example, and then we'll kind of talk about next steps. So for Mannings equation, I'm going to write it out. There's not really anything to derive. It has a similar format to the Shazy equation. And it's 1 over n, the hydraulic radius to the 2/3, and then slope to the 1/2. And this slope, well, you're going to go back and forth on this. If you use this equation in your career, we just did uniform flow where S naught is equal to SE under uniform flow conditions. But really, in what we did in pipe flow is this really should be SE. So we often substitute in S naught because we assume uniform flow in some situations. But ultimately we need to be putting the energy slope in there, or the slope of the energy grade line. So just kind of keep that in mind. Because under gradually varied flow conditions, we're going to be using this term. So this is for SI, and then V is equal to 1.486 or 449 over N, RH to the 2/3, S to the 1/2 for British gravitational standard. So this is the only term that changes. N is our Manning's coefficient. If you do any kind of modeling of rivers, you're going to be looking at tables of Manning's coefficients, there's books of Manning's coefficients. Right now at our stage, it's a necessary evil. I don't like it because it changes with flow depth, just like the F changes with flow with the Reynolds number, right? Your friction factor. Manning's is very similar. It's going to be, so you can imagine if you have this relative roughness, so we've got cobbles on a riverbed and we have low flow, then this roughness height relative to the overall depth height, this kind of, if this is our E and this is our D, E over D is going to be kind of, this is going to be relatively small. Oh, sorry. This is going to be, I guess, kind of relatively big. And then if we get a really big flow depth, then E over D is going to be small. So Manning's N changes with this, right? It's going to be, if this is rougher, we get N is bigger for rougher conditions and smaller for smoother conditions. And the Manning's N value, so N is equal to about 0.011 to 0.013 for concrete. That's about as low as it goes for like smooth concrete or like a plastic pipeline or something like that. And then N can be for like about 0.4 to 0.5 for natural channels. And then N can be 0.15 for floodplains, where you have veg, like shallow flow over like trees and sticks and stuff like this. So super rough conditions, you can get a much bigger Manning's N value for those kinds of conditions. So there's a table in your book for natural channels. It's different than the table for closed conduit pipeline. So we'll be referring to a different Manning's N table for this class. I like the Manning's equation and this coefficient. It's in the denominator, and so that means when you have a high Manning's N value, you get a lower velocity value. So rougher condition, slower velocity, greater depth. Low Manning's N value, faster velocity. So that's how that works. And that's, for me, that's a little more intuitive. High means rougher versus the Hazen-Williams coefficient, which is the opposite. So let's do just a very quick example, a very simple example. And I think I've got some more complicated examples posted on Canvas. We'll start with a very simple channel. We've got some water in that channel. And we've got a width of 3 meters. We've got a depth of 1.5 meters. And then we've got a slope a bed slope of 0.001. And we'll call this a concrete channel. So to given this flow depth and width, find Q assuming uniform flow conditions. So how do we do this? Well, we say, let's look at our Mannings equation. B is equal to, we are metric, so we're going to just say 1 over n, r h to 2/3, s naught to 1/2. This is very simple plug and chug. We can calculate our hydraulic radius, and what is that equal to, the hydraulic radius? Area over P. So let's throw that in there, 1.5 times 3 divided by, what's our wetted perimeter here? Okay, so 2 times 1.5 plus 3 meters. So we just do 1.5, 3, 1.5. So that's going to give us a hydraulic radius of 0.75. And I'll note that as you get a wider and wider channel, and you can plot this, the relationship between, if this is y, and then we're going to calculate hydraulic radius. Hydraulic radius converges to flow depth for wide channels. And I can't remember exactly what the depth to width ratio is, but you can plot this very quickly in Excel and see where they converge. I think it's maybe on the order of like 10 or something like that. So our width to depth ratio increases. So as that width to depth ratio increases, the hydraulic radius converges to y. Something to keep in mind. So sometimes, and we won't encounter this here, but sometimes people will swap in depth for hydraulic radius because that's simpler to calculate or to estimate. But that's only for like rivers, essentially, not for little canals and stuff like that. All right, Mannings N for a concrete canal, we can look up in our table. We'll say it's 0.013. And then we can use our continuity equation to, well, we'll just calculate velocity first. So V is equal to 1 over 0.013 times 0.75 to the 2/3, 0.001 to the 1/2. And then we end up with, I'm not using units here because the Mannings equation doesn't really work with units, empirical equation. So when you put all the numbers in like this, and this is going to be, meters and meters per meter, we end up with meters per second for velocity. So just have to keep that in faith. So we end up with, I didn't actually calculate, oh yeah, there it is, 2.01 meters per second. And then Q is equal to V times A. And we end up with about 9.0 meters cubed per second. Okay, not a hard problem, but the thing about this is we've got to make a lot of assumptions. And in this canal, is this like a perfectly sloped canal that's perfectly prismatic for a really long time? What if so, and if we want to assume normal conditions, we can say that we're at a normal depth. So I'm going to introduce that. It's going to be the last thing we introduce, a normal depth, or yn. And this is the depth at uniform flow. And say we have like a channel and there's like a spillway or something like that and the water spills over. We're going to hit our critical flow depth at some point over that. We talked about that. We'll actually derive this next week. But we'll note that the depth is like steadily increasing as you go upstream. As you go downstream, it's decreasing to go over to that spillway. And under this condition, we can say that, well, probably somewhere upstream, we're going to achieve our normal depth, where everything's in balance, but we know that there's some different boundary condition over here. And so the flow is kind of like getting faster and faster and faster. It's kind of accelerating as you well, not really accelerating, but in the X direction, you could say it's accelerating as it gets over this pour point. So at some point upstream, if everything's the same and prismatic, then we can approach this normal depth. So that's where this calculation could work. Alternatively, if we were to be given a discharge, a flow rate, so we know we need to move 9 cubic meters per second through this canal, how deep does that canal have to be for a given width? So you could use Manning's equation inversely to calculate the depth that is embedded in this term right here. So we have a flow rate, we've got an area, but that area is a function of depth. And I can't remember if rectangular, let me see here. I think in rectangular, it's a direct solution, but anytime you get to a trapezoid or something different, and it ends up being an iterative solution. And so you actually use solver in Excel to solve for a depth for a given flow rate in a channel. And so you basically have to iterate. You can just use solver to kind of loop it. And so you'll find, here's my flow rate. So then here's the depth that achieves that flow rate using Manning's equation. So you can get a little complicated.